Okay, so what we have here is basically, so it's medical quantum-inspired machine learning software. This is the migration of it. After very thorough review of this, it's definitely ready for implementation. So on the cover slide, so this is discussion 121. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device. This is Thursday, February 8th, 2024. So there's been a lot of these studies as far as using medical images in specific to, further, quantum machine learning. And this top one is basically patch-based medical image segmentation using MPS tensor state tensor networks. The advantage with using these is basically you get, you get, here we go. So here we go. You get efficiency with tensor networks, but you lose on accuracy. So it's an approximation. So that's just basically, how these things go. And what I did with this is I basically took a quantum transfer learning demo, scaled it up to 10 classes all the way to 44, with the 10 class showing about 11% increase over the previous ones. So yeah, it's, you're going to lose some off of time using these techniques. And what I'm going to be talking about today is to get the time back, more quantum benefit and faster too. And this last one is basically knee osteoarthritis. There's a whole, gamut of COVID images and brain tumor images and, also with Alzheimer's disease, Parkinson's that have been tested with quantum transfer learning in specific. And I'm getting down to, the detail of that. So the big news this week, while I was pulling all this together, is it's a very rare occurrence when you'll see IBM Quantum and IonQ get together. I haven't seen it happen before. The big news in the hardware side has been, last December, Harvard and QEra had this QPU with 48, qubits with some degree of error correction to it. It's kind of like the leading study right there. And what they did is basically similar research as what I've been showing all the time is using quantum simulation. They got 48 qubits to run orders of magnitude. It's actually 100, so 2 orders of magnitude better at lower cost as this using the Google Cloud virtual CPU machine. And they didn't stop there. So they kind of did a proof of concept that it was faster. It's obviously a lot cheaper to do it on, CPU, this, 112, virtual CPU kind of thing. And they went to 96, and 96 is double the qubits and reasonable speed and cost, and then using that same machine. And then after this, it went to 192 qubits. And then this particular one, and if you have been following this recently in recent years, they said it's impossible to get over 50 qubits on a quantum simulator. So they did it 192, which is, I believe, the benchmark for all this, using a combination of like 1,000 CPUs and 4,000 TPUs, with a runtime very similar to training a deep learning neural network, which is very involved. And yes, this is definitely a lot of hardware to get to this point, 192, but it's a huge thing because this is a single circuit. And yes, it's going to take up more RAM if we do quantum machine learning with this, approach, but we should at least be able to get to 96 qubits now instead of 30, where we're typically limited with PennyLane right now. So the 3 main areas I'll go over, and I think they're all going to see boosts, right? Because obviously the more researched ones are the quantum tensor networks, and pretty much everybody's run a quantum variational algorithm at some point for NLP or transfer learning or GANs. And I'm going to go in detail as far as the dequantized algorithms and just what it means as far as if we can rethink the way that we think about quantum inspired being just inspired by quantum mechanics and running, a simulated version of that into quantum inspired, meaning that we have these quantum algorithms. Now we're going to remove the quantum informations, that was inspired originally by the algorithms. And now we have dequantized algorithms, which, by the way, has the same class, or it's very similar to the algorithms that we have now, meaning that they're native bitwise to run on CPUs. Okay. So that's typically the way things go. If you have a quantum computer in the future, you want quantum data. If you have if you're doing quantum inspired right now, you're going to want the purest classical algorithm that was inspired by the quantum algorithm to run as fast as it can and as good as it can. So I'll go over these other things too, as far as, the the factors affecting growth in this, and you've heard me talk about software and hardware a little bit, that, both software and hardware is very likely going to increase at a good clip. And, we're going to see even higher circuits. But this 192 qubit circuit is something that everybody said was impossible, right? They said 50, the highest I can find is 62. So 192 qubit, which is, for machine learning, it's going to be hard to do it because it's taking so much hardware. But at 96 qubits, that's over twice as many. That's that's over 3 times as many qubits as we can run on PennyLane right now in a QML workflow. So I think that this is attainable using this IBM quantum INQ approach. And what's behind all of this is they call this instantaneous quantum polynomial algorithm here a white box, meaning that you can see inside it to a greater degree as opposed to black boxness. And it's over 100% faster than running a, end to end. Actually, it's not end to end. I'll get to that in a little bit. Over 100 times faster at a similar type of approach as, using it on a quantum computer. So why is all this happening is because QEra kind of took the lead late last year, and, IBM and INQ, obviously if the hardware's not here, and it's especially not going to be here for quantum machine learning, probably running single circuits, in the next, more distant years, or quantum data. If they can get quantum data, some of these dequantized notions don't hold. It's for classical data with dequantized. So anyways, with the quantum-inspired approach that IBM and INQ took, it was faster. So the Harvard one took 0.01 seconds for the unitary. 0.3 seconds was state preparation and measurement, which is what IBM and INQ are comparing it against. And then with post-selection and partial error correction, which, I think IBM and INQ gave the benefit of the doubt, 3 days, and it didn't do that comparison against the 3 days. So that's for the quantum computer. Now, for the classical computer, it's just taking a fraction of a second to do a 48 qubit circuit. And this is not super hardware. It's like 224 gigabytes of RAM on 112 virtual CPUs. So this, what it is, it's 0.3 seconds divided by 0.00258 is approximately 100 times faster, is where they get that number for the 100x. And if you've ever run these and you tried incorporating C0 or CZ layers, they're actually saying there's another table for a chart with this, no degradation, basically for, or hardly any degradation in adding these 2 qubit gates, which has been notoriously RAM intensive on quantum simulators. So, and again, you keep having to ask yourself, because this is a transition point in quantum computing. So, it's buying them time, because if they say that, hey, if we classically simulated this, we could still do a lot better. Plus our technology might, especially for, the quantum data or many, many years in quantum machine learning, because there's many things to fix with that. It's buying the 2 time because they have these, one is gate-based superconducting qubits, and the other is ion trap. So here's the details on 2x qubits. So again, the comparison was the 48 qubits. So at 2x qubits, 4 seconds. So I think this benchmark here is a good thing to shoot for. Now, keep in mind, not everybody has the same objective as making quantum-inspired machine learning as best as it can. It's kind of like they want to use it as a tool. So we're talking leading software platforms that aren't opening the gates to GPUs and these types of things. And, so basically the cost to simulate these, the 48 qubit, just basically, 0.0000328 cents. And yes, it took some time to develop classical hardware to this point, but we're just saying what's available now is much, much cheaper than you could ever run on a quantum computer, with hardware costs or cooling or whatever's involved. Now, the 96 qubit, a little bit more, but this is still a half a penny, so 0.00529 cents. Now, the magic behind all of this, I believe, is either in the software techniques that they use, if they use circuit cutting or mid-circuit measurement, qubit reuse, these things are known to exist, or if it's in the TPU. So the TPU in specific, you'll see at 4 times qubits, so that for the 48 and the 96, it took 112 virtual CPU, 224 gigs, more accessible to you and I, and it's like, it's not dirt cheap, but it's like $4 an hour, something like that. So that's where these figures come from, because if they can run really fast, then the cost is so low. So at 4x qubits, to get to the 192, now you're talking about substantial hardware to simulate, and 1,003 gigahertz, 62 core Intel Xeons. Nothing to, this is very serious classical hardware. 4,000 TPUs in parallel. And it took 4 days, which again, they're saying cost and time, very similar to what it would take to train a deep learning neural network. Not like a chat GPT, I don't believe. That would probably be, that's trillions of parameters, but you kind of get the sense of it. So I hope that sinks in as far as like the 48 qubit and the 96 qubit on very accessible hardware. For instance, like I might pay like $1.30, for a good GPU. So this is at like $4, to get up to 96 qubits basically. And the Clifford simulation test, they said in specific, took the TPUs. Now, if you know much about this, with GPUs, graphic processing units, they have tensor core units. So I'm thinking with the TPUs, they're kind of more direct as far as what's needed for processing quantum circuits. I have a hard time finding them, like on Google Colab, and they're cheaper, but it's not like this, like 4,000 TPUs in parallel kind of thing. So anyways, this study, IonQ and IBM, who are notorious for hardware, again, it's buying them time. They're going to have, things to back this up in the future, but it's just opening up the door. Like they're losing some because they're saying basically 196 qubits error-free with no decoherence, latency, or, especially differentiation issues, these types of things to do on just regular, classical computers. So you'll see this chart here. So as far as runtime between the 48 and 96, and then they, like I said, they did some of these side studies adding additional CNOT layers. And the IQP circuit is notoriously, it's going to be a lot more difficult than running an angle embedding or basis embedding or amplitude embedding because of all the CNOT gates. So that's what was so unique about this study, is because the circuit is relatively challenging, and going up with qubits with that too. So they say basically classical simulation costs may be difficult to meet, and I think this was a direct comparison to the QEra quantum computer due to power consumption alone. It's the state of quantum hardware. Now, I haven't found anything over, like I said, 62 qubits, and this is going to 192 qubits with like 5,000 combinations of CPUs and TPUs. And this is at least 3x qubits. So again, a quantum-inspired machine learning workflow is more intricate than running a single circuit. But the hardware that it took to get to 96, I think is within reach. Like it's physically possible if the software libraries don't hop on it. But it's physically possible to do, if that one took, less than a penny, with a runtime of around 5 seconds. So there's a Quantum Insider paper or as a review, and I take a look at them just to see what it's talking about, but this came straight from the archive. And this would probably be, a pretty accurate review. Are there any questions regarding this? Because this affects the whole industry, both quantum hardware, simulators, quantum inspired, these types of things. Are there any questions at this point? So again, the paper, I'll put it in the chat there, this 9, or afterwards, it'll be in the deck to use. So if there's not any questions regarding the study, I would definitely check it out because it affects everybody, right? This is a big thing. And so going on to the bulk of quantum-inspired machine learning here, and feel free to raise your hand, along the way, is if you're in quantum-inspired machine learning, you have to know about tensor networks. And it's a balance. You're trading off, like I said, there's an approximation factor behind it, versus efficiency. So you can run quantum circuits in tensor networks very efficiently. But the issue has been getting the most correct solution. They're not state vector algorithms like a typical circuit, but the thought is we need to fix the approximation issue with it, because we can get to a really high qubits with it. And I think at one point, NVIDIA is saying tens of thousands of qubits simulated on GPUs, their Q TensorNet with this specific one. So this gentleman is very open with the crowd. This is at UC Berkeley at Simons Institute, their workshop on tensor networks. And a lot of times, if you see some of these more recent talks, is they just get right into it, and they assume that you know exactly everything that's been going on in quantum circuit tensor networks the past 5 years. But this is a little bit older one, and that's exactly what he said. So in this upper left-hand one, when we think of a quantum circuit with qubits, left to right or top to bottom, however you want to do it, instead of doing it by time, now we're turning that into a geometry in the tensor network. So, time evolution of a quantum circuit now defined by the geometry of an MPS or, PEPS or whatever you want to do. And the quantum circuit, or the unitary, is now a linear map in it. And you'll see linear algebra all over these talks. And it says, basically, he at one point showed a specific formula up there, and he said that this in specific is what's causing this poor approximation with tensor networks. So if you get into tensor networks, you have to know that, because if you're not aware of that, then you do all the everything fits in there in a specific manner. You're basing on somebody else's work. It's synonymous. He says it's the same thing as approximating tensor networks. So quantum computation is the same thing as approximating tensor networks. So a lot of these things are there's probably been some development on this, but it's important to know that there's that trade-off to get high accuracy, safer classification. You might as well just run like parallel circuits, something very simple that's just giving more time to process an algorithm. So that's that specific one. Now this is another one. So this is Enshu, and this is ICTP Advanced School and Workshop on Quantum Science and Quantum Technologies. And this one's one of those more, we know about quantum many bodies, and he actually referred to it as few bodies, to the point where, it's just, as far as studying the system, it's very hard to study a many body as opposed to the points around a specific body. And he says it's motivated from systems starting, condensed matter physics, high energy physics, possibly quantum chemistry. So again, we're still on tensor networks here, and they're thought to be a huge breakthrough. And it's something like you can take your quantum circuit here or put it here, and you kind of have to know the limitations of it. But at that same time, if we can get to an acceptable answer, using a very high number of qubits, and potentially this IBM IonQ study helping it too, as far as reaching in these higher ones, then we can get better solutions, because we know tensor networks are efficient. Okay. Also, the IBM IonQ paper, that is state vector algorithm. That is not tensor network anything else. So that is defined by quantum gates. It's an exact solution that they get and calculate an amplitude for IBM IonQ in the first slides. And you will see this, in nature, entanglement exists, and that's why we have CX or C0 gates. And, I kind of discussed on that a little bit more. And we're also talking about, many body systems in the ground state should be local, that are local, should be distributed in a local fashion, right? So this is 2017. And this is a good talk, especially if you're in that high, the condensed matter physics, higher energy, physics is an efficient computational way to try to solve some problems. And I think that we'll see a lot, and this is the third of the tensor networks. This one is actually machine learning tensor networks, but there's so much, you're basically to go to the next step as you insert quantum algorithms. But if you look in the upper right-hand one, as far as this infinite MPS, locally purified states, PEPs, MERA, there continues to be developments in new tensor networks. And, the tools behind, such as when you're talking about machine learning, compressing the weights with some kind of tensor network to get more efficiency or better insight. So you see these techniques start to, build around tensor networks to, take advantage of the efficiency while losing some of the, while limiting the loss of the approximating nature of it. I'll have to update the figure. It does say Hoynell, which is for a different paper on that specific one. Are there any questions regarding tensor networks? Because a lot of times you just mention them and people, get super excited and they say, this is something that, a lot of people want to do. And then if not, so if you're up to date with the world in AI and machine learning, a lot of it's, natural language processing. So OpenAI, say for instance, they have ChatGPT, which does an excellent job, summarizing, multiple sites into a single answer. That's the generative part, generative pre-trained transformer. Is that instead of generating images like a GANs, generative adversarial network, it's generating, some text. So in the form of an answer like ChatGPT. So in the quantum version of this, so this is called from quantum pictorialism to quantum NLP and quantum AI. And Bob Kuka, by the way, he's had a lot of success, within quantum. He works at Quantinium. And this particular talk, if you join tomorrow mornings on the West Coast, it's called the Qiskit seminar series. The bottom gentleman is Zlatko, and he's also, I believe, PhD. So this particular talk kind of went through some introductory material leading up to this 2022 Nobel Prize with natural language processing. Now the quantum aspect of this is basically he read it to this gentleman talking about quantum teleportation, and he says, Bob, this is grammar. So it's very humorous to watch the slides, and a lot has been done in the specific area of QNLP. So Bob is represented over here in the left as this, skeleton figure. He has a good sense of humor. And, this was their first big paper, this mathematics foundation for compositional distributional model of meaning. And there was many other papers that followed suit. And obviously the big restriction is if you're doing IBM Qiskit is more, gate-based superconducting, and ion trap is they're still not there. But the software continues to be developed. And it basically says this: if I tell you a sentence which you never heard before, but you know the meaning of all the words, the grammatical structure makes sense, this process can be applied to quantum circuits. And the ones that I chose, and it gets into Alice and Bob and these types of things, and they become quite humorous. But the one I'm going to talk about is, so on the top left, the pawn next to a king that a knight can capture is here. Okay, and then its representation in a quantum circuit is here, okay, at this bottom one. This middle one, the ostrich next to a tree that a cheetah next to grass can capture, it appears to be efficiently represented the words inside of the gates. So as this all evolves and, the chat GPTs get bigger and llamas get bigger, another AI kind of chatbot, is that you'll see this, continual interest with it with quantum. So we do have a hand raise. You can go ahead, Harold.
I can't see your screen if you're sharing. I don't know if it's a me issue or.
I see the screen.
Yeah, I think it's showing.
I see it as well.
Okay.
Yeah. Yeah. So, and if anybody has any questions at this point, but, he has a big team. I think at one point he said 60 people, or Zlatko said, and there's a lot behind this as all these technologies, evolve. And obviously I'm going to be using classical processing methods. In Forbes, Cambridge Quantum makes quantum natural language processing a reality. Quantinium enhances the world's first quantum natural language. Now, the other thing that's really important, and this is a universal statement, is he said that there was a long time where he couldn't talk about quantum. He couldn't talk about anything to get it into the headlines as it related to, natural language processing. But as we see it now, is NLP is going to be a huge area, and it already is. And as everything gets bigger to the point, simply Googling a search, experts say, will be, efficiently, getting that information on the spot instead of the model, being pre-trained every month or two or however often they do it. So this is I would say there's a lot of effort and a lot of energy behind the QNLP. And as far as the papers, I would definitely check those out. So they're always going to be, highlighted by, the limitations that they can do with classical simulation. And like I showed earlier today is, now we're up to 192 qubits for a IQP circuit, which was thought to not even be in the discussion. So quantum transfer learning for digital image processing, this one by Chen, KC. This is UPM, Quantum Computing Technology, February of 2023. This demo, short of it's just being awesome, yes, there's lots to fix with it, but if you have a data set, this is a Penny Lane demo. If you have a data set, you can very easily, and you know how to code a little bit, you can very easily use your own data set. So you see here, he uses, the CT scan, and this was during COVID. And, obviously I've worked on this model too, and I could kind of pick out things as far as, I could, make this better, or, your algorithm here, that type of stuff. But he used COVID-19 medical images and this pre-trained image net into a deep learning neural network and then to a quantum circuit, okay? So everything up to this point with variational quantum algorithms can likely be optimized some way with dequantized algorithms. That's the way everything's moving. It's called QSVT, or quantum singular value transformation in particular, has been dequantized. So meaning if we're taking the benefits that we learned from quantum and then now we remove the quantum mechanical information, there is no state preparation to go from classical data into a quantum circuit, okay? We were inspired by the quantum circuit, but now it's all classical, right? So that's where everything's going, and that's reflective in the first paper there too. He did do a good job with qubits, and kind of similar studies that I've done, varying variational layers, batch size. But if you want to just get your feet wet with quantum and quantum transfer learning, I would highly recommend this demo. It's a Penny Lane. It's just called quantum transfer learning. And it helps you to understand, the elements going into a quantum circuit. And again, this is, it likely has to get updated to get better performance and to get better speed, if I were to go back to it. Now, what does all this look like? So when I talk about quantum circuits, you're typically talking about embedding some classical data, processing it, in this quantum, these quantum layers inside of the CPU or GPU, and then you measure it, and that measurement goes back into zeros and ones. So this process is computationally demanding, and some circuits, for tensor networks and variational quantum algorithm applications will likely stay, in converting classical data into quantum states inside of the CPU or GPU, and then back into bits. But you can see this is a good example here. Most of the quantum GANs, I believe, just address the generator. I haven't seen too many that are both as far as the demos, but I think in literature, you could probably find more substance if you're looking to, this is generative adversarial networks, meaning that you're generating some fake images based on some information of real images. So it's basically the GANs process, but this is just an example of kind of what's out there as far as generator discriminator. And here we go. So this is probably the thing that's going to help quantum inspired the most. And again, I think when people are designing circuits and they're working on applications and these types of things, and either it's too slow, which is often a case, or your accuracy is not there, or say if I ran it for longer epochs with all classical, I can do a better job than, doing it with just a better quantum approach or better quantum circuit. So this gentleman, Sivag Garabian, so this is Munich Center for Quantum Science and Technology Conference of July of 2022, does a good job of summarizing this. And he says, where's the boundary between the power of classical versus quantum computers? So what we're essentially talking about is, if you want to, capture this on some quantum, computer versus capturing it classically with bits, with this highly evolved systems of GPUs and TPUs, it's more and more seeming like a lot of these algorithms can be dequantized. Now, the next step in all these is the usability. So they're different, right? They don't run the same, those types of things. And I think that we'll, at some point, probably get automation, as far as taking quantum circuits or, different parts of the quantum, tensor networks, taking the quantum information out of it, turning it into a classical algorithm, and then you don't have to deal with, converting into quantum states, okay? So you can't talk about dequantized algorithms without mentioning, the other people that have developed this. So Yu and Tang in specific, this has been her project in her PhD work, and I'll lead up to the dissertation that she created. But it's all about this QSVT, quantum singular value transformation. And it was, Guyan, Su, Liu, and Wiebe. You'll hear about them. And it's like a Swiss Army knife, is what they say of quantum algorithms. So anyways, if you can get between here and polynomially slower, then the algorithm is deemed dequantized, meaning that it's proven to not have an exponential advantage over running it on classical systems. And this particular, and again, I'll remove that, kind of figure there that's not Hoyne. This particular presenter, he says he's working on this conjecture, quantum PCP conjecture. He hasn't been able to prove it yet, like with the QSVT. But from my perspective, there's not a ton of people that are focused on this. But it's just, if it gets to the point that we're just dequantizing all quantum algorithms and just, running them on classical, that's a good alternative. But the definition of quantum inspired changes. Now we're just, we were inspired by that algorithm, but now it is a classical algorithm, like a pure classical algorithm that's faster to run many times. So this is Yu and Tang. So this is at the, UC Berkeley Simons Institute. So you saw the first one I presented on, that also was at Simons Institute. And, she says, so basically, given the success dequantizing QSVT, can other quantum-inspired algorithms be unified with linear algebra? And, many QiML algorithms run in polylogarithmic in dimension, assuming strong input assumptions. So if somebody claims that, your application is running awesome now just because you substituted a quantum algorithm in it, it may have a strong input assumption, meaning that it's biasing towards the quantum algorithm, but it's not necessarily meant that the quantum algorithm was best in that case. So the dissertation I've read through, not the whole way through, but a good portion of it. And the other thing to keep in mind is, this is all classical data, right? So if there comes time with a quantum computer in the future between machine learning and quantum data, I don't know what'll come first, but they all seem like they're far out, right? So this is all, if a given input data is classical, there may be no exponential speedup available for the quantum algorithm. There's other types of speedups, but typically dequantized means there's no exponential speedup on a quantum computer compared to a classical computer is typically how that's defined. So this is the dissertation, and I recommend it to anybody. So if you're going to be using classical hardware, this is a really good place to start. It's relatively recent. So, I believe she probably graduated last year. And her, along with other, panelists, have been on these other, Qiskit video series, these types of things. And, so basically, if there's any questions here. So yeah, so okay.
I'm
Go ahead.
asking because some people by QML they mean quantum data that in fact quantum properties of some particles, for example.
Yeah, it's basically, I mean, if you can capture quantum data from a quantum sensor, that's believed to be the main way of getting it. The issue is there's no effective way to store it at long term. So, it's probably going to be increasing, but the last time I checked, maybe like milliseconds or microseconds that you can get it from a quantum sensor, but it just can't be stored for any usable time. So that's what's meant by that. That's because that's how we collect data is we have sensors and but we can store them into like an SSD, for hundreds of years, stuff like that. So that's the issue, with the quantum computer is basically, besides the machine learning stuff, is it's native to quantum data. So when you go through the process of converting classical data to run on a quantum computer, that's inefficient. Just like it's inefficient to run a simulated quantum algorithm on a classical computer without dequantizing it. Any other questions? And, so basically there's only two pictures in this longer, all dissertations are long, but this on the left was what was believed to be the exponential speed up landscape to run on quantum hardware before her work started. Okay, so this is at University of Washington. Now afterwards, this is what was determined: sparsely based QSVT. These on the left have a better chance of exponential speed up to run on a quantum computer than these other ones. So they're actually in the same positions and just drawing this line here. So it means multiple things. It was a huge blow to quantum hardware because it was thought that principal component analysis, support vector machines, and these are very well-known researchers that have come up with these. It was anticipated that they would lead to exponential speedups on quantum hardware. So, that's been the shift. Is basically the other issue with quantum computers is, will there be a quantum algorithm around that will still have exponential speed up by the time they actually do start to work? And like I said, if it's quantum data, in the future, like 7 years or something like that, where we can collect it, from sensors and then hold on to it and use it right away, or store it for longer periods of time, these don't apply. So none of these apply. This is just for classical data. Okay. So that's the hope right now. I think the biggest hope for quantum hardware is the quantum data. But as you may know, most of the data that we have is classical, and we can store it for very, very long periods of time. Okay, so basically the first, and if you missed the first part, I would definitely check it out. It's this new archive paper. And again, the magnitude of it is very great. Like, very often, if any, do you see a collaboration between two quantum hardware companies using quantum simulation on CPUs and TPUs to create results better than their competitor that's on neutral atom. So, like I said, it's buying the industry time as far as quantum computers, but it's not. It still doesn't look great. I don't believe, for quantum computers, because due to all this algorithm, losing exponential speed out on a bunch of them, and not having quantum data, and not differentiating well for machine learning, the things are just stacking up against it, more and more. So we'll see, because I think what this will come down to is, yes, it'll be a combination of both, both classical, to process, and both quantum to process. But the edge, unless quantum data has a huge breakthrough, appears to be with simulating, the circuits, because now it's shown close to 200 qubits, which is over, 3 times as much as anybody imagined before the study. So in a complicated circuit, an IQP circuit, it wasn't just like an embedding or anything easy, So this is the new state of the industry is, yes, there'll be more hardware developments, but the pace that quantum-inspired machine learning will move at with machine learning and not having a whole host of other issues will likely outpace the development, I believe. So software and hardware techniques will continue to advance. So circuit cutting is basically you can cut the gates left and right, or you can cut the qubits up and down. Mid-circuit measurement, qubit reuse, and these are some of these have been established with hardware. Using parallel neural networks, these types of things as well. And if you've missed it, so this is all a migration. So I think that the industry is ripe enough, and a lot of this is based on that Hoyne et al. Paper. It's a quantum-inspired machine learning survey that talks about dequantized algorithms, tensor networks, quantum variational algorithms in much detail. And I think that we're going to start to see this migration, with the technology, with quantum inspired to start heading into medical. And, so basically the things to inside QiML, because I've been talking a lot about comparing between, hardware to quantum inspired, is it's the rate of these dequantized algorithms developments, they may increase. And removing quantum information allows for utilizing classical data directly without having to do any state preparation, which is known to be, it's basically taking, if you have an image, it's converting that classical image into quantum states. Now you don't have to do that. It's a classical algorithm again. And then, basically, if you're really into designing, quantum circuits, tensor networks, applications with quantum circuits, you really want to be aware of dequantized, because if you're using, say, for instance, a quantum algorithm that's just, it's going to run slower on classical hardware as opposed to something that's been dequantized, then that's a huge benefit that your competitors may have, right? So again, I think a lot of this just takes a different train of thought. Like a lot of us were thinking quantum inspired was, a full representation of a quantum circuit in a classical computer, but a dequantized algorithm probably won't look anything like that. And like I said, the issue with quantum variational algorithms are slow, and that, we'll likely see, increased efficiencies with kind of these linear approaches that use bits the whole way through, instead of converting to qubits and these types of things. And I saw there's some other things. So where can I find QNLP links from a screen? So I'll include them in the deck. It'll be up on LinkedIn. And yeah, so I would follow the Bob Kuka of Quantinium. I would definitely follow that group. There was a thing where Oxford, I think it's Oxford Quantum Circuits, OQC, they were acquired by Quantinium. Quantinium is Honeywell based, and they focus on ion trap quantum computers. So I would definitely follow them because they've had a whole series of papers that have been released. And you'll probably find good information because a lot of times if they weren't able to simulate up to 192 qubits from today, they were running it limitedly on simulators, right? Or they tried it on ion trap or some other technology, but the software is what counts because the software is there. And then as we get more RAM for GPUs, more bandwidth, it allows you to do too much stuff. So it tricked me too. So there was a question here. So if you search for Kuka, that's how you pronounce his last name, into YouTube, you will find a lot of presentations. And he's well connected with the rest of the industry too. And QNLP is, likely going to be a big thing, depending on your hardware approach. I don't think anything, maybe like small applications to begin with, saying like, oh yeah, for sure, run this, dequantized algorithm, this type of thing here, instead of, doing it the old fashioned way. So I think, some breakthroughs there. Any other questions? Yeah, so I think the moral of the story is there's a lot to look forward to, so as we get into, this migration is basically, it's been a process, and there, like, I can't stress enough, you have to read, if you want to do anything on classical hardware with, starting with quantum circuits, you have to read it's Quantum Inspired Machine Learning, a survey. And it's the Hoyne et al. That I'll have to take care of on the other slides, but it does a very orderly account of the three main areas, starting with dequantized algorithms, variational, and then tensor networks, and then variational quantum algorithms, and some other ones too, but very highlighting the things that I was presenting today. Say for instance, if they say, this particular person's dissertation, and it has a huge impact on the rest of the industry, right? Like the future of running algorithms on which device, kind of stuff. So if you want something that's risky, but it'll probably pay out, and you have a good math background, it's definitely the dequantized algorithms. I would definitely do that. And it on its own field will likely help, it's our approach to tensor networks and QVA circuits, those variational algorithms. Any other questions? So yeah, the deck will be up, and I can't stress enough, like, it's really important to run your experiments. I got really into the brain tumors and getting high into classes, making it more challenging, and parallel circuits and these types of things. And then, you have to know what's going on overall with the industry, right? So, if you're looking at 28 penny lane QML demos, and they all kind of have a similar approach, as opposed to maybe, substituting a particular part of that quantum algorithm for, dequantize. And like I said, that's still developing as far as the practical application of dequantized algorithms. But there's hope. And I think, the main thing is basically, if you think of, like, when you brought the circuit into a classical computer, it was brought with bits. So why can't you just figure out what all that meant and then turn it back into bits? So that's the theory, right? So what has to get better, and I think there's been at least a couple other papers that have said the practical application of the understanding the dequantized algorithms and using them still has to improve. So, but it all comes down to native. You should use classical data on classical computers with classical algorithms, and quantum data with quantum computers. This is like 101 kind of stuff that's taught, the first couple of weeks or whatever, as far as getting an advantage, right? Like, try to stay native. Any other questions? And, if you have, and it's best just to do it now. So if you have specific things you're working on in quantum, you can ask a question. I could try to help. And I've seen a lot as far as demos and, QNLP and QGANs and quantum transfer learning. But feel free to ask, because it can save you months of research doing the mainstream, approach of, not all this coming out, which is important that it's coming out. Anybody that we haven't heard from? So, and Anastasia, you could ask any more questions, or Tucker.
I don't have any question.
And then if not, Martin or Diego. So Harold has a question here. So doesn't QiML have two possible increased speed and better predictions? Yeah, I mean, the main thing is it's machine learning with a quantum circuit. So now you're parameterizing a regular quantum circuit. So it really depends on the application. You're not specifically guaranteed, to use a specific algorithm every time and then you get advantage. So, because I've been looking at it very microscopically, as far as like this algorithm, if it runs natively classical, but it was derived from, quantum, these types of things. But yeah, I mean, doing it a traditional method, I get over 11% increase versus a classical model. There's other things going on. So when you ask a question like that, it really just depends on how the algorithm started. Like, is it known to be quadratically faster, polynomially faster, exponentially faster, those types of things for speed. And the second part is like utility. So say, for instance, like if you did run a quantum circuit here that, say we haven't devised a way to dequantize it, now you're looking at a different utility of an algorithm, that's possible too, right? Because, it's a mindset. It's like if you were doing convolutional neural networks and deep learning AI, and then you switched it over to transformers, there's a lot that's different between them. One is like a sliding pane that goes over the image, and the other one places attention on certain parts of the image. So for quantum circuits and for quantum processing, it's a different way. If you have a block sphere and you're turning it, and your parameter is a rotation on the qubit, these types of things. And I'm not sure. So Harold also asked another question. Have you done anything with QBoost? Not as much, and I hear about it once in a while. So this gradient boost, and feel free, you can come on to ask or explain it a little bit better, because I haven't gone that far into QBoost or gradient boost, but I do hear about it. Because what it reminds me of is, go ahead, Harold.
Well, it's just the things we're looking at are all better predictions. Honestly, we don't care if it's faster. But if we can get a 2% better prediction on something that's millions of dollars, that is a lot of money.
Yeah. Yeah, the thing that comes to mind, so this is in Penny Lane's kind of their code notebook kind of thing, is you go through and there's specific optimizers that are specific towards, quantum. And I know with Qiskit, QNRG, these types of things. And it's worth part one is to experiment with. So if you have something and you're switching to, QBoost from gradient boost, it's worth doing. Just as a simple industry fix, it's just like, okay, we'll take it without a full analysis and academia kind of thing. It's worth trying.
Are you familiar with what the Saudi Arabian oil company is doing? But it's the national oil company. They've implemented quantum machine learning for doing reservoir predictions, where to drill, how to drill, how much is really in the reservoir. And they're saying they have return on investment using quantum machine learning today.
Yeah, it's very possible. Again,
it's better predictions. It's not faster.
Yeah, I've
just better predictions.
A fair amount of projects, and what it boils down to is like when they say there's a strong assumption on inputs. If you're running a quantum circuit and now it's better, if it works in industry, that's fine. Use it. I guess the point that I'm trying to make is that if you start fundamentally with something like just removing all quantum information from the quantum algorithm, now it's proven to not be slowed down by preparing states. That type of stuff is where I'm at. But I think the things that you're talking about, they're all valid, and they could say we got better whatevers. In academia in specific, it has to be tested like 10 times, like over and over. And I think the long-term growth will come more from something like that. But it's absolutely, if that's what they're claiming, it could very well be. Typically, if you have like a loss efficiency, where you say you have a single algorithm compared to two in parallel, the two in parallel are placing more processing time on the algorithm as opposed to the whole QML process, then that's valid. And I proved that before. But yeah, it's a type of thing. Yeah, just you experiment it. And like I said, the ones that'll last the longest is if you can prove it from the beginning, this algorithm has this specific, speed up versus the previous one, and it works in your system too.
Okay, thank you.
Yeah. And any other questions? So I did want to comment on this. So QHack, which is Penny Lane or slash Xanadu's, their annual conference is going on as of today. So I'll just type in here. So Penny Lane is, I mean, you should know how to spell that. But if you look at QHack, which is just the letter Q, and then HACK, they started today. I caught one of the sessions, and it's starting to heat up a little bit, I would say. Tomorrow, with Friday, and I think it goes through part of next week too, they start to have a lot of good speakers that, say, for instance, might work on, they'll probably have a Q on LP. If it's not Bob, I don't know who it is, or Bob Kuka. So they have very subject matter experts that are working in specific areas, right? I mean, some might talk about hardware, but I think a lot of them, based on previous years, I think there's at least 3 Q hacks that they've done. Their application, so how can we use quantum, on CPUs or GPUs, that type of stuff is what most of them are going to be. But I would definitely check that out. And the other, so there's another question here too. So Anastasia says, never heard about the QML. Yeah, so I think that's been going on for a little while. This is the thing that Harold was talking about. So basically using it in oil production stuff. And like I said, if you can get it to work, that's great. In industry, it doesn't have to be like, it's not like academia where it's just rigorously tested before it moves on to application. If you get better results and it's not proving to be to harm anything, change the optimizer, change the quantum circuit, these types of things. Model recommendations.
That is true, but realize, they had spent what, 20 million on hardware before they ever got a QML result that was positive. And now they've paid back all of that plus more. So it's not like, if it's not paying back, they wouldn't be saying there was ROI.
Yeah, I'm not doubting.
Yeah, it's not proven like academic is, but when you can prove it with money, it's not something that's not worthwhile.
Mm-hmm.
Even for you and for us medical, if you could make predictions on cancer 1 or 2% better, wouldn't that be a game changer?
Yeah, for sure. And there's things with time. So if I can run a quantum circuit and I get better results than the classical counterpart, but it was taking me maybe 7x on time, then I could use that 7x on the classical model and do other things. So that's where it'll come down to, because time is money. So you can get better performance using a lot of quantum circuits. And, a head-to-head comparison would say, well, if both models ran and you gave both of them 10 minutes, where would they be? Or could you use that time more efficiently on the classical model? So it's a rigorous thing. But as a drop-in replacement, if you're just saying, like, we're changing this to this quantum, now we have this, and it's getting the results, cost, loss, efficiency, is better, then you should do it.
Now, generally, you're only using quantum to train the model. Once models are trained, from what I understand, most of them then run live predictions on classical hardware.
It just depends. It really just depends. If you're talking about inference there,
yeah,
I don't know, like, what was the data set that they're training on, or how many pieces of data, these types of things. But everything comes out over the course of time. So I think the biggest thing is if you can prove in your own specific case that we don't care if it runs longer, you're not going to get the efficiency that you want. The end result is it ran in good enough time with some portion of quantum, then you should use it.
Right. We have some predictions we're going to run once a month. Others are run once a week. Some run once a day. Others, the inference has to run immediately, but it doesn't matter how long. For once a month, it doesn't matter how long it runs. If it gets better predictions, you get better predictions. And if it's still worth the investment in the hardware to get better predictions, then that's return on investment.
Yeah, so there's
Trust me, ROI will drive quantum so much faster than academics. Once there's return on investment, there's going to be so much buying and so much production. You won't understand. It would be going to be like generative AI. If somebody hits the ground with quantum machine learning that has better predictions, I mean, the billion's going to triple, in weeks.
And so there's some other questions here. So Martin says, any model recommendations for quantum transfer learning? If you look on GitHub, type in quantum transfer learning like you just did, and then they're mostly imaging. So actually mine, I think I got the biggest, I was up to 4,400 images, 44 classes. So that's a good model. My 10 class, you'll see 10 class, like 3,500 images. I got like 86%, which is 11% better than the classical model. That's up there. That's up on mine. So, and I see here, one sec. So yeah, there's a lot on GitHub with QTL. Like I said, it's just a very user-friendly model. As far as getting your data set in, it's Andrea Marie is the one that did it. And then, you can like or share the GitHub here. I just put it up on the chat. They also do stuff with BERT, which is like text and QTL. So all of these things, there was several years of development with it. And like I said, like without understanding the fundamentals as far as like this specific, circuit, shouldn't take so much time to get to that performance, but you can get to it with quantum. So if you choose to go that route, that's fine. I'm just saying it's going to be a lot better, especially as we remove quantum information from circuits and now they run native, classical, processing inspired by quantum, but, more native. I think that's where you'll start to see the breakthroughs. And let's see, anybody that we haven't heard from? And, definitely keep it posted. So I also put up on LinkedIn, so it's the migration guide. And then it goes through, there's like, I don't know what it was. Like there's probably 15 things that Quantum Inspired hasn't worked out. The main things that are missing is GPU support if you're using PennyLane plus PyTorch or TensorFlow. So that's a big thing that's missing. And then the RAM issue with computers, but the Qiskit, IBM Quantum and IonQ appears to be working on that quite well, right? So it's getting the qubits up and running them. So I would definitely check that out. It'll kind of like see what's real. What's real is what people program with. And it works like adjoint diffration, just different things that'll work on CPUs and GPUs. So awesome. Any other last questions or comments? And I appreciate everybody coming on, and definitely keep tuned for next week as I really see all this kind of heading to industry. This is discussion 121, Thursday, February 8th, 2024. And this has been medical quantum inspired machine learning, this migration of it. I thank everybody for coming on. Have a good rest of the night and have a productive rest of the week. Take care, everybody. Bye.